Yeah. Hello, everyone. My name is Joshua. It's my pleasure to welcome you to this tutorial on cointegration analysis. Cointegration is an econometric concept which mimics the existence of a long-run equilibrium among economic time series. If two or more series are themselves not stationary, but a linear combination of them is stationary, then they are said to be cointegrated. Previously, the usual procedure for testing hypotheses concerning such relationship was to run OLS regression on data which had been different initially. But with the development of cointegration framework, there have been tremendous improvements in the approach. There are three methods of cointegration analysis. One is Engle-Granger method. We have Phillips-Ouliaris method. Then we have Johansen. I'm going to run us through the three methods. We're going to start with Engle-Granger. Let's load the packages that we actually need. The first is URCA, which is Unit Root Cointegration Analysis. Then the other one is forecast. Let's load the packages. Beautiful. Let's go through the data we want to use. The data is RAOTBL3. The data set can be found in the URCA package. So let's run the data and load it. To know details of what the data is all about, you can just put asking question here, the name of the object. So I run this. Beautiful. So we can see clearly it's a data frame with quarterly data from UK in 1966 April until 1991 February. In terms of the variable, we have the real consumption expenditure, real income, real wealth. Then we have DD6H2, dummy variable for 1968 February. Then we have dummy variable for 1979 February. Then we have dummy variable for 1988 March. To remind us of the column names again, you can just type names here, then you put the objects in brackets. You run this. So these are the column names again. So let's quickly look at the summary statistics. We use summary tools package. So let's run the package. Beautiful. So I call the summary statistics sum stats. So with our objects, DESER is the function in summary tool. So these are objects. Then I say produce common statistics. That's why I have stats equals to common here. So let's run this. And we may want to look at our results on the console. I think, so let's view it. Remember, if you type view, you may have view in summary tools, view in utils package, but please ensure that you pick the view. We start with the small letter in summary tool, that view, sum stats, and file equals sumstat.doc. If I run this, it's going to export it straight to Microsoft Word. But let us first look at the answer on the console. I type sumstat and run. So here is the answer. So let me, oh, beautiful. So let's go up. So here we are. So we have all the data, all the variables. So we have mean, standard deviation, minimum, median, maximum, and the number of valid observations. Yeah, like I said, if you want to export it to Microsoft Word, then you use view. I think that is super simple. And if you have done that, that sumstat.doc will definitely be located in your working directory. So let's run this. You can see the setup file written. As you can see that it has been exported to my directory. The next thing you want to do is to declare the variables as time series. So we pick them one by one. So we have the consumption, we have the income, we have the wealth. So you start 1966 April up to 1991 February. Then it's a quarterly data. That's why we have the frequency to be 4. So let's run this. All right. So let's run it up to line 40. So beautiful. The next thing is, let's plot the variables and inspect for stationarity. This possibility of stationarity. So I combine all the variables using C-bind, and I name it TS data. So I have C-bind consumption income weight here. So let's run it. Good. So I need forecast library in order to auto plot. So I say library forecast. So library forecast. Okay. Then auto plot here. So auto plot. So beautiful. So we have, this is our graph. So clearly it appears that consumption and income are actually moving together. Why weight is another story. It's telling us something different, actually. So we still need to proceed to carry out some other tests rather than depending solely on the interpretation of our graph. Okay, so let's move. So I have test for normality. So I use Shapiro. So I have Shapiro test consumption, Shapiro test income. So let's take it. Hey, sorry, it's taking me too far. All right, so I have Shapiro. So let's run it. Yeah. Don't forget the normal hypothesis for Shapiro is that the data is normally distributed. So, and if you look at the p-values, all the p-values are less than 0.05. So you reject the null hypothesis. And in that wise, the hypothesis of normal distribution is rejected for all the variables. And that's super straightforward. So the next thing we try to do is to test for the unit roots. So let's try to do that at levels. Okay. So stationarity test at levels. We are using augmented Fuller test. So let's start with consumption. We are using AIC, that's archaic information criteria, as our selection criteria. There are other ones we can use. We have Bayesian information criteria. We have a lot of them. So FPA, final prediction error, all sorts of things. So it depends on your choice, but at least try to indicate the one you have used and why. So we start with testing for the unit root around constant and trend. So that's why we say trend here. Let's look at the summary. So you look at the summary here, you can see that at 1% is minus 4.04, 5% minus 3.45. But if you look at the test statistics, minus 1.378, confirming that the data is not stationary. So we try to have the unit root around, to test for unit root around the constant alone. That's why we say type equals to drift. So you run it, you get a summary. Yeah. can see the same conclusion. We have the same conclusion. Then even when you remove the constant and the trend, you put none there. Let's try it and see, maybe we can get something better. Yeah, let's get the summary here. So when you look at it, so you can see that no matter what we've done, it's clear that the data is not stationary. So we try to do that also for income at levels. So this income at levels. So and let's see, we have the same conclusion. You can see -2, -4 here. Then we try to do that also for wealth. So, and we have the same conclusion. So summary. So here we are. So let's check it. Yeah, beautiful. Yeah. Now we know that all the variables are not stationary. So trying to run your relationship, the linear combination using OLS, even when you know that it is not stationary like this, is what is described as running a spurious regression. So run it, we see it will appear as if there is causal relation. You can see that. You can see the income and wealth. You look at how they are highly significant. And you look at your R squared is 0.99. You want to say, wow, but that is spurious regression. So now that to avoid the problem of spurious regression, the next thing we need to do is to generate the first difference of each variable. So let's try to do that so that we test for the stationarity at first difference. So I call it SC2, LI2, AW2 for income and for consumption, income, and wealth. So let's run this. Yeah, beautiful. So good. Okay. Then we test for the stationarity. So we run it. That's get the summary. So for consumption, for instance, you can see it's -6.29, which confirms that the variable is stationary at first difference. So we try to repeat that also for income and wealth. So let's quickly do that. For wealth, let's do that. Yeah, you know. And then if you get the summary, you can see that. So we can actually confirm that the variables are stationary at first difference. So now that we have I1, that is, the order of integration is 1, that is, they are stationary after first difference, all the variables. So we can now proceed to the Engle-Granger two-step procedure. So I try to combine all the variables, consumption, income, and wealth here. So I run it. So, and I try to obtain the possible 3 linear combination. We have consumption as function of income and wealth, income as function of consumption and wealth, wealth as function of income and consumption. So those are just the 3 possible combinations we can possibly have. So I run this. Wonderful. So yeah, I want to produce everything in just one table, so I use Stargazer. So you run this to get your output in your directory. So yeah, beautiful. So it's already in my directory as eg that that is so. So let me check it there. eg that, so this is it here. You just need to right click here, then to say open with. So you open it with Microsoft Word very quickly. So this is the equation here. So you can see it clearly. So this is So this is what we are saying there. So, but you can still, you cannot still explain this as long-run relationship until you have confirmed by testing the residual, that is the error for stationarity. So in this case, we extract and store the regression residual. So I call it this the residual for the consumption, income, and wealth. So, and to extract it here along everything. Beautiful. So you come here. So, and you try to carry out some tests, because normality test. For instance, you use Jakibera. So I have Jakibera for the three of them here. So Jakibera test. So you run it. Oh, sorry, Jakibera is a T series package, so that's not so. Okay, so let's go over it again. Yeah. So I run this. So beautiful. So we check, and the hypothesis of, if you look at it carefully for all the variables, you can see that the hypothesis and the null hypothesis of normality of the residual actually is not rejected. So there's no problem. Again, we try to carry out conditional heteroscedasticity tests. So I think we use FinTS here. So we use hash tests. You can do that also for the other variables. So this is it here. Also, this is confirming that we don't have the problem of conditional heteroscedasticity. Then we have the jump box text for autocorrelation. So we try to do that also. So don't forget, we have to repeat that also for income and consumption. So this is, you can see that here we have a little problem because this is actually showing that there is problem of autocorrelation. And when you discover problems of autocorrelation, it's actually pointing to the kind of problem of misspecification. So that's why I say, okay, let's proceed and test for misspecification of the model. Yeah, try to use LM test to reset an LM test. So I try to do that for the first equation for consumption. Yeah, and this actually confirmed that, yeah, we have misspecification problem. So, really serious. So what do I do? Very, very simple. You know, you have all this dummy for policies. So to me, it's better you augment your model by adding those dummies. But we are not going into details of that. You can do that on your own. But we need to test for the unit root of the residual to be sure that co-integration test is rejected or not rejected. So we try to do that for consumption here. We run it. So we get the summary here. Oh, sorry. So sorry. Yeah. Okay, I get the summary here. Summary. So beautiful. You can see that the value of the stats minus 4.14 compared to the critical value. So you can see that there is co-integration. So that's fantastic. So you can plot it at least. So, okay. Sorry, I've not run the CLI. All right, so I run the CLC before, so let me run this. So beautiful, you can now see, you can see the residual, you can see that it's mean reverting, you can see the ACF and PACF, so that's fine. So now that you confirm co-integration, then the next thing is to try to obtain the error correction model so that we can get the deviation from the equilibrium to get. So we have, so you get the first difference. So that's what I say, diff in consumption income weight here. Then you try to get the lag of your error. Then I combine everything. Then I run my regression. So it's beautiful. So you have to do it here. So this is, yeah, so it's beautiful. So this is what, this is just the short-run dynamics that you have to explain. I hope it's very, very clear. So for Phillips-Ouliaris, cointegration test, we have two types. We have variance ratio tests. It's very, very straightforward. So since we already have our EG data where we combine consumption, income, and wealth, so you have your PU test, that is for the variance ratio. So you may use constant, so then type. So you run this. Then you get the summary. The summary will actually show us whether there is cointegration or not. So you can now see, if you look at the value of test size 58, and if you look at the critical value, whether at 10%, 5%, 1%, you can see that the test size is actually greater. So confirming that you have cointegration. So there is long-run relationship among the variables. So that is very simple and straightforward. You can see the equation. So you can change, one thing with Phillips-Ouliaris is that it picks the first variable as independent. So which means if you want to run it for income and weight as dependent variable, then you have to rearrange our EG data and do it again, which is very straightforward to do. The other one is multivariate trace statistics. So that one is what is called PZ test here. So let's run it. So we get the summary too. So beautiful. And you have the same conclusion. All right. The last one is cointegration using Johansen procedure. And in addition to URCA, we will need VARS, then DPNYR, and DG+2 packages. So let's run the packages we need. I run this. So fine. So in this case, I want to use Denmark data. That Denmark data also is in URCA. So I run it. You want to get details of what the data is all about. Let's try this. So it's a data set for Denmark. It was used by Johansen and Phillip-Ouliaris, those guys that actually discovered this, that developed, the Johansen procedure. So in terms of the variables, you have the, it's a data frame with 55 observations. You have real money, you have real income, then you have price deflator, you have bond rates, then you have bank deposit rate. These are the variables of interest. And some of them are in log forms. Yeah. So you try to select variables of interest. I want to drop entry. So that's why I say percent greater percent. So that is using the pipe operator in GPLY. Run this. Beautiful. So like before, we need to convert our variables to time series. That's exactly what we are trying to do here. So the starting point is 1974, January. So let's try to do that for all the variables. Good. So beautiful. Okay, we still have to do that for IBO and IDA. So that's nice. So, and like before, I think we need to combine the variables Let us, since we are familiar with C bind, let us use C bind. So that's C bind. I prefer C bind, so that's good. But you can actually use TS, so that's beautiful. Right. So library forecast. Yeah, it's possible auto plot is somewhere else. So I will need to add forecasts. Yeah, so that I will know that I'm using auto plot in forecast package. So I run this. So beautiful. So these are my graphs, and you can actually discover that the graph is actually showing that the variables are not stationary. So again, like before you perform your ADF, so I try to do the ADF straight away at levels. So these are at levels for the variables. So, and if you look at all the variables, you can check they are not stationary at levels. So again, I try to perform the ADF unit root test at first difference. So that's what I try to do here. So, sorry. Okay, yeah, beautiful. So, and if you check the variables, all of them are stationary at first difference. So for Johansen, we have two different statistics. We have the eigen value, maximum eigen value, then we have trace. So it's the best thing is to try both and draw your conclusion. So I start with the maximum eigen. So the function is ca.jo, is Cointegration Johansen. So this is our data set. So, and you define your egg depth. So that's whether it's norm, drift, or trend. So the spec will be long run transition. So I think since we want long run relationship, I put long run here. So let's run this. So let's try to get a summary. Yeah. So if you look at the summaries that comes out with so many things here. But the starting point is to look at whether there is co-integration or not. And you try to look at that by looking at the R values. You have R equals to 0, 1, 2, 3. So R equals to 0 is the null hypothesis showing there is no co-integration at all. So, and if you check that test statistics is 31.51, and if you look at the critical values, it's actually greater than that of up to 5%. So you can now say clearly that the null hypothesis of no co-integration is rejected outright. So at least you now want to know, maybe you have how many linear combination can you actually discover. So we move up to 1. 1 is that the null hypothesis is that you do not have more than 1. So, and the alternative is that at least you have more than 1. So, but if you look at it, this 10.15 is less than all the critical values. And that's why we do not reject that hypothesis, which means we just have just one co-integrating equation. So, and since you have just one co-integrating equation, that's very, very simple. So you look at the normalized co-integration relation. But on the safer side, since I already know, to get my short run, because definitely since co-integrating equation exists, then you have to obtain the vector error correction model. So it's very simple to do. So you have the function is CAJORLS. So this is the model we have run. And we have how many co-integrating equations? Just one. That's R equals to 1. So I run it here. So then I get a summary. So beautiful. So here is the summary of the, so you can see the short run dynamics you have. So you can explain that one very simple to see which of the variables actually affect what. In terms of the long run, this is the long run. Yeah, but for this long run, you can see that is a minor adjustment that we need to do, because here guys, we can't get the standard error or the t-value. So that's why we need this function that has been developed. So using library text reg here. So I run it directly from here to, sorry. Okay, yeah, let's me run finish here. That's good. So run. So now the long run is this. This is the long run. So beautiful. So, and I can get it in a better form by getting the screen reg. So you run it, yeah. So here is showing you clearly that the relationship between LRM, which is the real money, as well as demand for money. If you look at the relationship with income, with bond, so on and so forth. So it's very, very straightforward. This is the long run equation. And you have the standard error there. So, but in case you do not have this, the last aspects of what I want you to pay attention to what I want to say. For a vector time series modeling, a vector autoregressive model is used for describing the short-time dynamics. When there are presence of long-time equilibrium relationships, a vector error correction model, just like the one I explained, is used. We use VECM because we have cointegration equation, so which consists of the VAR and the error correction equation. So when all variables stationary in level, we use VAR with stationary level variables. When all variables are not stationary in level, we use a VAR with stationary growth variables. So when all variables are not stationary in level, and there are some co-integrations in level, we use VECM model, which consists of a VAR with stationary growth variables and error correction equation. Don't forget this with not stationary. So let's say at the end of the day, we did not get co-integration, which means we have to revert to VAR in order to get the short-run dynamics. So the starting point is to determine what's going to be our lag length. So we use VAR select in order to do that. So run this. So the summary will be up. So look at the criteria. You can see 2, 1, 1, 1. So maximum is actually 2. So the lag length is selected by using AIC, HQS, and so on. Lower these scores are better, since these criteria penalize models that use more parameters. So we've used VAR select function in order to get the maximum lag length. Now, we can proceed to estimation. There are 2 ways to proceed. You can actually convert the VECM to VAR. We use VEC to VAR function, if that is what you want to do. Or since I already I've loaded my VAR package, I can actually use my VAR to run, which is what I'm going to do. So whichever one you prefer, to me is okay. So here I have my VAR model. So this is VAR. Then maximum lag 2. So type constant. Ceasing, don't forget it's quarterly, so that's why I put 4 there. So I run. So you can get the summary of, yeah, so here you find the summary of your short run dynamics. So then as usual, we have to perform some tests. So you test for heteroscedasticity, that's hash test. Then you test for normality, Yakibera. Then you can make a forecast. Let's say I want to forecast for the next, let's say 12 quarters. You know, it's quarterly variable now. So I say my N or equals to 12 here. So that predict, I say predict this, N ahead. So this will give me, you can see all the values, the predictions. So these are the predictions. But I prefer to use my forecast. I use forecast. Forecast give us a better shape. So let's say I use forecast this and say it's equals to 12. The same thing. And I may just have my VAR underscore F here. So let's run this. Well, beautiful. The reason why I love this forecast is going to tell you all those 12 that you have, the forecast you have made, 1987, quarter 4, 1988, quarter 1, there's going to give you the point forecast and sort of this. You may want to plot it, very straightforward to plot. You can auto plot or just plot directly. So here are the forecast. So then the last thing is, in case you shock any of the variables, then what's going to be the effect on the model? So we try to, that is what we are trying to do by obtaining the orthogonal impulse response. So I think, so we just plot it, it's RF, our model. We already say that we are projecting up to, we are using 12, so 12 periods, so that's wrong. Good. So, and you can now see, because this is LRM, so this is LRM to LRM, LRM to this real money to real money to income, to bond, so on and so forth. So then the next thing we just need to do in order to get other orthogonal impulse response, just eat. You can see this is LRY. Eat again, this is IBO. Eat again, this is ID. So that's everything you need. To me, I think this is almost all you need to know about co-integration analysis using R. Thank you for your time. And this is where we are going to end this class. We will meet again. Thank you.